Alright, so I'm going to make a stab at doing section 1.3. This is actually going to be my second stab at starting 1.3 because I wasn't so happy with my first go about. So the section is called Continuity. And let me give a definition and then explain what that definition is before I get into the section. So we say, or I say, or it's said, that a function, we'll call it f of x, is continuous at x equal to some number, we usually call that x equal to a, provided three criteria exist. One, the function is defined at that value x equal to a. Second, the limit of the function at x equals a exists. And three, the function value at x equal to a is equal to the limit value. Those might not make any sense to you right now because they're just abstract definitions that make a lot of sense to me, but I've taught math for enough years that should make a lot of sense to me. So what I'm going to do is try to make a more generic definition for you and then try to illustrate these rules through some examples before we get into the homework. So all these three rules in terms of understanding, it boils down to this. We say a function is continuous at some value of x provided I don't have to lift my marker to draw the graph above or below. Could be below that value of x. So if when I'm drawing my graph, I have to pick up my pen to draw like two halves of a graph, the value beneath the graph, the value on the x-axis where I have to do that break, we'd call that a point of discontinuity, and the function wouldn't be continuous at that point. So let me go through a few examples that aren't in the homework just to get us warmed up for the homework. So I'm going to wind up drawing 3 or 4 graphs, probably 3. I'm going to ask the question, is the graph of the function f of x, each of these is going to be a graph of f of x, a different f of x each time, continuous at, make a nice number like x equal to 3. So now I'm just going to draw an x-axis and a y-axis, and because I'm focusing on x equal to 3, I'm going to really hammer down the 3. So here's where 3 is. And as I draw the graph, if I have to lift up my pen when I draw through x equals 3 and draw kind of two halves of my graph, that's not continuous there. So let me start a nice graph like this. I'm going to draw up to 3, make an open circle, and then jump up and make a closed circle and make the rest of my graph. So this function right here, it's not continuous at x equals 3. And I knew it's not continuous at x equal to 3 because right above 3, the graph I'm drawing is the blue graph. The dotted line is just to help you focus on the x equal 3 part of it. It's not continuous at x equal 3 because I had to lift up my pencil to draw two sections of the graph above x equals 3. So this function isn't continuous at x equals 3 because I had to lift up my marker to draw the graph above or below that point, below x equal to 3. Now knowing it's not continuous at x equals 3 is nice. Now which of the reasons does it happen? Well, is the function, so now when we get into the homework, we have to say which of the 3 reasons makes the function discontinuous there. Well, is the function defined at x equal to 3? It's defined at x equals 3 because there's a closed dot above 3. So it's defined there, so that reason isn't the reason it's not continuous. Does the limit of the function exist? Well, the left-hand limit is some number down here. The right-hand limit is some number up the y value of that point. So the left-hand limit is the y value of this point. The right-hand limit is the value of the y coordinate of that point. Because the left-hand limit and the right-hand limit aren't the same, the function's limit doesn't exist at that point. So the reason this function isn't continuous at x equals 3 is because the limit doesn't exist at x equals 3. So this is not continuous at x equals 3 because the limit as x approaches 3 of this function f of x does not exist. So a function is always, if it's discontinuous or it's not continuous, it's always going to be not continuous for at least one of the 3 reasons. Our goal is to find the reasons it's not continuous if it isn't continuous. So that's case 1. This wasn't continuous at x equals 3 for reason 2 because the limit didn't exist because the left hand and the right hand limit aren't the same. Let me make another picture and ask the same question. Is this function continuous at x equal to 3? So I'm just drawing just random pictures here to illustrate continuity. So again, here's the x equals to 3. And as I draw my graph, I'm just going to draw, keep drawing, get to 3, and keep drawing again. So because when I drew the graph through 3, I didn't have to lift up my pencil, I'd say the graph, or the function, is continuous at x equal to 3 because as I was drawing the graph, I didn't have to pick up my pencil to segment the graph into pieces. And if a function is continuous at a point, I don't need to say anything. I just say it's continuous and move on. So this function is continuous at x equal to 3, and that's the best thing that we can have happen. Let me make another picture. Again, I'm going to focus on this 3. And I'll draw my graph again. So I'm going to draw. I'm going to get just to the left of 3, and then I'm going to continue drawing. And I've created a hole. A lot of times when a graph has a hole, I put an open circle on that hole But when my calculator draws a graph like this, it wouldn't put a hole. Let me show you a function that would have a graph like this. Like if on my calculator I graphed, this would be something like, I don't know, x plus 1 times x minus 3 divided by x minus 3. Let me do a zoom standard. Zoom standard. And that looks a heck of a lot like the picture I drew. I don't see the hole, but there is a hole there. Let me focus in on the hole by tweaking my window. I'm going to make my x-min go from 2 and my x-max go to 4 to focus better on that range. And let me see if I just make that change, if that would be good enough. So I'm going to change my window, x-min to 2, x-max to 4, redraw the graph, and you can barely see it. Oh, heck, it looks horrible. Let me make my y smaller. Make my y's from, I don't know, y min 0, y max maybe like 4, and maybe the graph won't look so horrible. Oh, it's not high enough. I needed to make my y max, so I'm just playing here, so how about 3 to 7? Because I didn't prep this ahead of time. It's a little bit funky getting the right window so you could see the hole, but I want to just, we've done graphs that have had holes before, and there it is right there. Here's x equal 2, x equals 3, x equals 4. There's a hole. So to draw this graph, I draw one half, pick up my pen, I draw the other half. So this graph right here is not continuous at x equals 3 because, well, that's what we need to say. So it's graph. Usually, if I'm drawing this by myself, I'd write a hole in there, but it really doesn't have a hole. I just draw that hole in to emphasize that it's there. So this graph is not continuous at x equal to 3. And why isn't it continuous at x equals 3? Well, one of 3 things. Is the function defined at x equal to 3? Well, I go at 3 and I look up. I don't see any closed circles, so the function's not defined there at all. So it's not continuous at x equal to 3 because it's not defined at x equal to 3. To be defined at x equal to 3, then somewhere above 3 there'd have to be a portion of the graph that exists, and an open circle isn't a portion of the graph. Should I do one more of these? It's already 13 minutes into the video. Let me just start jumping into the homework. So what the homework has is the first 10 problems are a set of graphs. That's what I'll get probably in this half of the video. And what I have to do is find any places where the function has any values of x where the function is discontinuous, which means any value of x that if I was drawing the graph, I'd have to lift up my pencil to draw 2 halves of the graph. And once I find any point of discontinuity, I'm going to tell you why it's discontinuous. So I'm going to do number 2, and then you'll do number 1. They're real similar. So in number 2, to draw this, I'd go up to this point, I'd draw the solid circle, and then I draw the rest of the graph. So this function right here, if I'm drawing it, I have to lift up my pencil once right to get to that dot, and then again. So I had to lift up my pencil twice. And the value of x that I had to lift up my pencil to do the portions is right there at x equals 2. That's the only segment of the graph that I had to lift up my pencil for. So this is not continuous. It has a point of discontinuity. So saying something that's not continuous, it means it's or I can say it's discontinuous. That's the same as not continuous in a bigger word that I can't really spell. At x equal to 2. And that's the only place where my graph isn't continuous, because that's the only place where I have to lift up my pencil to draw the graph. Now, which reason? Region 1 says the function isn't defined at the point of continuity. Well, It's defined at x equal to 2 because there's a solid dot above x equal 2. So that reason isn't good for me. The next reason, the limit doesn't exist. Well, the left-hand limit, so if I was doing the left-hand limit would be the y-coordinate of that open circle, and the right-hand limit would also be the the y-coordinate of that open circle. So the limit exists. The function's defined at that point. It's this value here. The limit exists. It's the y-coordinate of that. So the first two don't go. The third thing must be the reason it doesn't exist, why it's not continuous. The limit doesn't equal the function value. The function value is the y-coordinate of that point. The limit value at the point of discontinuity is the y-coordinate of that point. The y-coordinate of the function value and the y-coordinate of the limit value are different, so it's for reason 3. So it's it's discontinuous or not continuous at x equal 2, and it's going to be reason 3. So you should be able to make a stab at number 1 and see where that takes you. And now I'm going to go on and do problem 4. And my problem 4 should be just like your problem 3. So I look at my graph. For number 4, to draw this graph, this whole region of the graph, I wouldn't have to lift up my pen. I could even draw that solid circle without lifting up my pen. And then I lift up my pen and I draw this part of the graph. So the place where I had to lift up my pen is that value of x, and that's microscopically small, but that's at x equals 1. So it has a point of discontinuity, or it's discontinuous, or it's not continuous. So it's discontinuous at x equal to 1. Now, what reason is it? I have 3 choices. The function isn't defined at 1. Well, it's certainly defined at 1 because there's a solid dot above 1. Second, the limit doesn't exist. This is where I'm golden, because in this one, the left-hand limit is the y-coordinate of that point. The right-hand limit is the y-coordinate of that point. Because the left-hand limit and the right-hand limit aren't the same value, then the limit doesn't exist at that point. So it's discontinuous at x equal 1, and the reason is going to be for reason 2. The limit doesn't exist at that point of discontinuity. Your question should have that same sort of vibe to it when you do question 3. Alright, so pause the video, do question 3. I'll move on to question 6, which is a mess. So when I look at question 6, it's the graph has a bunch of pieces to it, many more than yours maybe. When I go to do this, I draw up to here. I lift up my pencil. As soon as I have to lift up my pencil, I get a point of discontinuity. So the first point of discontinuity is at x equal to negative 4. Because at x equal negative 4, I lift up and I start drawing again. And the reason it's discontinuous here, the function exists because it has a solid dot above x equal to 4. It's discontinuous at x equal to negative 4 because the left-hand limit is the y-coordinate of that point, and the right-hand limit is the y-coordinate of that point. So the limit doesn't exist because the left and the right-hand limit aren't the same. So at x equal to negative 2, it's discontinuous for reason number 2. Let me continue drawing. This point right here, I wouldn't have to lift up my pencil to draw, so it's continuous there. And I come all the way down and I get another break. At this break right here, I'm going to have to go and start drawing up here. So there's my next point of discontinuity, and that's at x equal to 2. And it's the same reason. The left-hand limit is the y-coordinate of that point. The right-hand limit is the y-coordinate of that point. The left and the right-hand limit aren't the same value. So that's what reason 2 says. Reason 2 says the limit doesn't exist. The left and the right-hand limit aren't the same. I continue going, I get this open circle, and that open circle wouldn't really, it really would be a break in the graph like that, and I'd have to lift up my pen to draw that. So open circles are breaks in the graph where I have to lift up my pen to draw. So that's the last point of discontinuity. That's at x equal to 4. And the reason it doesn't exist, it's discontinuous at x equals 4, is because if I look above 4, there isn't a closed circle anywhere above 4, so the function isn't defined at that, because the graph has to exist. There has to be a closed circle or a portion of the graph that goes through that point. So that's reason 1. So you should make a stab at number 5, and it should work similarly. It's going to have just 2 points of discontinuity for yours, and you're going to get a reason 2 and a reason 1. Just like I have 2 reason 2s and a reason 1, you're going to get 1 reason 1, 1 reason 2 for yours. Graph for 8 is not stellar. Zoom this in a little bit. But if I look at this, as I draw my graph, I draw this half. This vertical asymptote I just drew in here. It's not part of the graph, but it's a vertical asymptote like we learned in college algebra. So this whole half of the graph is continuous, and this whole part of the graph is continuous. But there's 2 halves of the graph, the bottom half and the top half, and it's discontinuous at that value of x on the dotted line, and I think that's at x equals 2. It's discontinuous at x equal to 2 because I had to lift up my pencil to draw the second half. So it's discontinuous, or not continuous, or has a point of discontinuity. They all mean the same thing, at x equal to 2. And the reason it's not continuous is because if I go all the way above and below the graph through 2, the graph doesn't exist there. That's reason 1 again. The function isn't defined at a vertical asymptote. When you have a vertical asymptote drawn with a dashed line, the function doesn't exist for that value of x. So when you go to do your problem 7, it's just going to be the same thing. You have 1 point of discontinuity, and it's going to be a decimal actually. And it's going to be reason 1 again because the function doesn't exist on vertical asymptotes. Ten's exactly the same sort of thing as 9, and this is a little more readable. Again, if I'm drawing 10, I have this half of the graph, lift up my pen, draw this half of the graph. It has a point of discontinuity, and that point of discontinuity is the x value of that. And I think here's x equals 1. Oh gosh, I can't tell. It's a cruddy graph. Here's x equals 1. I need to know the x coordinate of that vertical line, and I'll be danged if I could tell you what that is. I'm going to call that 2.5 because here's 1, 2, and then maybe 3 and 4. I'm going to call that 3.5 and just hope that that's actually what it is. And so I'm going to say there's a point of discontinuity. So it's discontinuous at x equals, and I'm calling that 2.5, but maybe it's not really 2.5. And same reason, the function doesn't exist at vertical asymptotes, so it's going to be reason 1. Right. So in the second half of section 1.3, we are asked to find, given an equation, the where the function is discontinuous. And the nice thing is, fractions are always only discontinuous where the denominators are 0. So most of the problems give me a fraction and they ask me to find the points of discontinuity. So the points of discontinuity, the values of x, where a fraction is not continuous, are the values that make the denominator 0. Because functions aren't defined where the denominators are 0. So in problem 12, I could sketch a graph and get you the point of discontinuity, and I'll do that in a second. But to find the points of discontinuity for any fraction, you just take the denominator and set it equal to 0, just like the algebra to find the domain of a fraction. So problem 12, it will have a point of discontinuity at x equal to 5, and the reason is going to be reason 1 again. The same reason that we just used for problem 9 and 10. It's going to be reason 1 because a function isn't defined at that point. So it's going to be reason 1. If I graphed this, you'll see it just fine. You'll get a vertical asymptote at x equal to 5. So let me just go ahead and graph this real quickly. I'm going to go y equals clear. And I know the graphs are so hard to see, so I try to push this close, and I don't know that that really helps. But x plus 1 in parentheses divided by parentheses x minus 5. I'm just going to do a zoom standard. And you'll see you get the 2 halves of the graph. And right at x equal to 5, there's a vertical asymptote there that my calculator doesn't draw in. But right at x equals 5 is the first half of the graph goes right up to x equals 5. At 5, I lift up my pen and I draw the second half of the graph. So it has a point of discontinuity at x equal to 5 because there's a vertical asymptote there. And at vertical asymptotes, the graphs aren't defined. So for every fraction problem between 11 and 28, it's asking me to find the points of discontinuity for a fraction. And any place where the denominator is 0 is going to be a point of discontinuity. It's all going to be for reason 1 because the function isn't continuous there. Sometimes the points of discontinuity will be asymptotes, sometimes they'll be holes. And I'll point out the difference to you, but it's not terribly important. So you'll do 13, I'll do 14. I find the points of discontinuity for any fraction by taking the denominator and setting it equal to 0. Because this denominator has a square, I have to factor it. Factors into x plus 1 times x minus 7. Then I set the contents of the parentheses equal to 0. And I get 2 points of discontinuity. So the points, or the values of x, so it's discontinuous. We'll say it's discontinuous or not continuous at x equal -1 and 7. And again, it's going to be reason 1 because the function isn't defined at those values of x's. Let me just graph this real quickly so you can see. There's going to be a vertical asymptote at x equal -1. There's going to be a vertical asymptote at 7. So if I go y equals 2 divided by, let me clear this out first, 2 divided by parentheses x squared minus 6x minus 7 zoom standard, you're going to see, oh, that doesn't look like a zoom standard. What did I do so badly? Y equals 2 divided by x squared minus 6x minus 7, x plus 1, x minus 7. Really disturbed how that graph looks. Zoom standard? Better. I must have not hit zoom standard. It's a cruddy looking graph, but right here at x equals -1, you have a vertical asymptote, so the function's not defined there. And right here at x equals 7, you have a vertical asymptote and the function's not defined there. So the reason the limit doesn't exist, at x equals -1, I draw part of the graph, I pick up my pen, draw the rest of the graph, so I have to lift up my pencil to draw the graph, so it's discontinuous there, and the function doesn't exist there. keep going down at x equals 7. I continue my graph, pick up again, draw the rest of the graph, and the function again doesn't exist at x equals 7 because there's a vertical asymptote there, so that's a point of discontinuity. So for all fractions, we'll get points of discontinuity where the denominator is equal to 0. Those points of discontinuities will either be wholes or they'll be asymptotes. And it doesn't really matter if there's a whole or an asymptote because the function's still reason 1 is not defined there. 15 and 16, they're going to have a point of discontinuity. When I do problem 16, to get the point of discontinuity, I take the denominator and set it equal to 0. So it has a point of discontinuity, or it's discontinuous. At x equal negative 3, and it's reason 1. This one actually has a whole as opposed to an asymptote, because if I reduced the problem by factoring and canceling, the asymptote will cancel out and create a whole. So there's actually going to be a whole there. So if I graph this function, y equals clear parentheses x squared minus 9 divided by parentheses x plus 3, and hit a graph, I might not see the whole because the window's not conducive to see the whole. So it has a hole at x equal to negative 3. So to see that hole, I need to tweak my window. I'm going to make my x min go from negative 4, my x max go to negative 2, and my y's, I don't know, negative 5 to 0. And now you'll be able to see that hole. So, well, if I picked a good, I didn't apparently pick y's very good. Let me make my y's, I'm playing right here because I don't know. I thought I could have guessed, but not. There's the hole right there. It's at x equal to negative 3. And the graph isn't defined at a hole. It's not defined at a vertical asymptote. So reason 1 is still a perfectly good reason to say why the function has a point of discontinuity right there. To get any reason other than reason 1, I'd have to make a piecewise defined function. And some teachers love piecewise functions. I just don't think they're that important. They don't really come up at all in our course, so I didn't want to get into those points of discontinuity using the other reasons 2 and 3, because you'd have to have really bizarrely defined functions to get that done. So for number 18, I'm finding the points of discontinuity, the values of x where the function isn't continuous. Take the denominator, set it equal to 0. I'm going to factor this. I get x equal to negative 1 and x equal to 3. If I took the time to graph this, one of these is going to be a hole, one is going to be a vertical asymptote. So it's discontinuous at x equal negative 1 and 3, both reasons 1 again. Function isn't defined where the denominator is equal to 0. Should do the same for 17. I'm going to skip doing 20. It's exactly the same thing. You're going to factor the denominator, and the values of x that make the denominator 0 are going to be the values of where the function is discontinuous, and it's going to be reason 1. 21 and 22 are, however, tricky, so you should pause the video and do 19. I'm not going to do 20. For 22, I'm going to take and set the denominator equal to 0 to find the values of x where this graph is not continuous. And that doesn't factor, so I'm going to minus 25 from both sides and solve by square rooting. So I get x squared equals to negative 25, square root plus or minus square root. So I get x equals plus or minus 5i. So this is only discontinuous for imaginary numbers, which means it's continuous everywhere, because it's only discontinuous on an imaginary graph, and we graph real numbers only. So here, there's no points of discontinuity, and we're going to say it's continuous everywhere. And I'll show you this graph here in a second. So this graph isn't going to have a hole, nor is it going to have a vertical asymptote. So let me take a stab at graphing this, just so you can see that it doesn't have a hole, nor it doesn't have a vertical asymptote. So I'm going to go clear 3 divided by parentheses x squared plus 25. I don't really know what this graph is going to look like. I'm going to hit zoom in standard. So zoom in 6. I'm not seeing anything because that's a cruddy window. Now, I'm not sure what the window should be. I know my x's aren't bad, it's my y's that are messed up. I'm going to hit second in table real quickly and peek at the y values. You look how small the y values are. They're in the points. So in order to see this graph well, I'm going to need to make my y's really small. So my y min is going to be maybe 0, and my y max is going to be maybe like 0.1, and I think that will get me a better picture. You don't have to graph these, but it's just maybe nice to see the graph, to see that y min 0, y max 0.1. It's just nice to see that there's no breaks in the graph. So here's a better picture. I didn't get up quite high enough. Let me go a little bit higher. 0.1 wasn't high enough. Let me go maybe to 0.5. And there you can see perfectly the graph doesn't have any breaks in it. It's continuous everywhere. So you're not required to graph these at all, but it was probably nice to see what I did. So when I graphed and I don't see, when I pressed my graph and I did zoom standard and I didn't see a darn thing, I knew that my y's were definitely a problem. Maybe my x's were both a problem. But I started attacking my y's by hitting second in table and looked at the values in the y column. The values in the y columns had decimals in them, so I thought I needed to make my y's have decimals, and they were all positive. So I popped to my window, I made my smallest y positive, which is 0, and my biggest y have a decimal in it, and then I magically got a much better looking graph than not. But I didn't have to graph if when you set the denominator of a fraction equal to 0, if you get an I in your answer, then there aren't any points of discontinuity and the graph is continuous everywhere. 23 and 24, I take the denominator, set it equal to 0 to find my points of discontinuity. That's prime. That's no good. So either I'm going to use a quadratic formula or completing the square, and I don't like the quadratic formula. Somebody is completing the square to solve this. Quadratic formula I'm going to use because it's the easier way to solve this. Easiest way probably. I need to remember the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. And now I'm going to plug the numbers in. So I'm going to get x equals fraction, b with a negative sign in front of it, so negative 4 plus or minus the square root of b squared, which is going to be 4 squared, minus 4ac, which is 4 times 1 times 7, all over 2a, which is 2 times 1. So this is going to give me x equals negative 4 plus or minus the square root, and then I'm going to get 16 minus 28, because 4 squared is 16 and 4 times 1 times 7 is 28, and 16 minus 28 is negative 12 over 2. That gives me x equals negative 4 plus or minus the square root of 12 times I over 2, because when you have a negative under a square root, you can drop that negative and make a positive under the square root by producing an I outside the square root. Just like in problem 22, in my efforts to see where the denominator is equal to 0, my calculations produced an I. that means that graph is going to be continuous everywhere and there's no points of discontinuity. So for my answer, I could either say there's no points of discontinuity, or, which is equivalent to saying it's continuous everywhere, and that's what I'll say. So it's continuous everywhere. And there's no more algebra to do than that. So you should make a stab at 23. I think it's probably going to be the same thing. That 38 in the denominator is going to make your, it's going to make some really large numbers. You may have to pull your calculator out to do 23, but that's okay. The rest of the section's slam dunk, super easy. There's only 2 more even problems. I could graph this without a calculator, but I'll graph it with my calculator just to show you what I need to show you. So this is 3x minus 2. Again, let me zoom in a little bit and hit enter, zoom, standard. This is just a lovely line. Lines don't have any breaks in them. So the graph for number 26, if I was doing this, I'd go down 2 on the y-axis, and then the slope is 3, which is 3 over 1. You don't have to remember this right yet. So up 3 over 1, draw the line, and that graph I can draw completely without lifting up my pencil. This is considered a polynomial, and polynomials are continuous everywhere. Problem 25 and 26, because they're polynomials, the graphs are going to be unbroken. In fact, I knew this was going to be a line, and I know I can draw a line without picking up my pencil. So I should realize what the graph looks like, and even maybe know how to graph it. But I knew I can graph this. I knew it was going to be a line, and I knew it's just one fluid motion without picking up my pencil, so it's continuous everywhere. There's no points of discontinuity. There's no algebra to do for 25 or 26 because there isn't a fraction with a denominator. So to find the points of discontinuity for a polynomial, there's no algebra to do. Polynomials are continuous everywhere, and it's going to turn out for 25, 26, 27, and 28, which are all polynomials, and there's going to be no algebra for these problems. And the answer for each of problems 25, 26, and 27, and 28 is they're going to be continuous everywhere because I'll be able to draw the graph without lifting up my pencil. So your answer for 25, you can draw a graph and say, well, it's only one continuous graph. I didn't have to pick up my pencil to draw 2 segments, so it's continuous everywhere. There's no points of discontinuity. Hopefully when you look at 27 and 28, you know what shape the graph is. In 28, it's going to be a parabola. I can graph that on my calculator. So if I graphed clear x squared minus 4x minus 5. You learn how to graph these in some other classes. The graph looks beautiful. It's just a beautiful parabola. I can draw that entire graph without lifting up my pencil. So this is continuous everywhere. The fact that it's not a fraction, the fact that it's a polynomial, it's continuous everywhere. So again, for 27, which is also going to be a parabola, and 28, which is a parabola, there's no algebra to do here. So since it's not a fraction, and it is a polynomial, it's continuous everywhere because there's no breaks in the graph of a parabola. And that's the whole section. So hopefully you're able to do these problems. I know that when I took my first calculus course, I could do the problems, and I thought I understood everything, but I really didn't understand so well the concepts. And it's completely okay if you don't completely understand the concepts. As long as at this point you're able to do the problems and get them correct, that's kind of where you need to be. You kind of need to be a class or 2 beyond this class for all the topics that we're doing now to make complete sense to you. They'll make a little bit of sense right now, but if you take Math 218, they'll start to make a little more sense than they do now. So it's just you have to, if you can just do the problems, you're doing well enough for right now.